Uh, Hi, welcome to a video on this LT-SPICE simulation. In this video, we'll see how it is the working of these two 555 timers. So, if you carefully observe the two configuration of these two 555 timers, so the first one is you can see there is a trigger signal, there is a pulse that is given having on time as 2 millisecond and total period as 4 millisecond. So this is the waveform and its amplitude are plus 5 volt and minus 5 volts. So typically you have a square wave of plus or minus 5 volt amplitude, and on time is 2 millisecond and total time is 4 millisecond. That is used as a signal to trigger the 555 timer. So naturally this is a mono stable multivibrator. So the RTCT, that is timing capacitor of this monoshot, is R1 C1 here, having the values as it is given here, and we are not applying any external control voltage. It is just 2/3 VCC, and this is the connection done for mono stable multivibrator. If you carefully observe, the output of this is actually going to the reset pin of 555 timer, which is there now configured in a stable mode. So in a stable multivibrator mode, this reset is not permanently connected to VCC, but it is connected to the output of the monoshot, meaning when the output of the monoshot is high, then only it will oscillate with a certain frequency and duty cycle as decided by this R3, R4 and C3. And when this output is 0, the output of this stable multivibrator will also be 0. And again you can see this control voltage is not connected with any external voltage. So it's again 2/3 VCC is your VTH, VTL is 1/3 VCC. The main contention here is, so we are controlling the output of this 555 timer in a stable mode using a reset pin, which is being reset using the output of the monoshot. You can observe one more thing here, that trigger signal is not directly applied to this trigger pin of 555 timer, but it is passing through a signal conditioning circuit comprising C2, R2 and D1. So let us spend some time on this. So if you can see here, this is the circuit what you have. So this is the trigger signal what you have given. So that is V trigger, which is something like this. This is 5 volt, minus 5 volt, and having 2 millisecond and total time is 4 millisecond. So the purpose of using this particular circuit is to make sure that we are generating spikes out of this particular signal. Now since it is connected to VCC, the output will be there at VCC, clamped to VCC, and if this is your signal, when it is going down, it just goes down and it again goes back, and when it is rising here, this is how it goes. This is the thing. In order to get these type of spikes for this type of input, the must condition is RC should be far less than T. That is, there is a of course in the circuit you have it as R2 C2, that should be far less than T. This T, that is 2 millisecond. Suppose if you can see what are the values that I have connected there, just go back there and find out. So the value of R2 is 100 ohm and C2 is 0.01 microfarad. If you find that value, it comes out to be 100 multiplied by 0.01 exponential minus 6, so it is 1 microfarad. So it is 1 microfarad is far less than 2 millisecond. See, this is what we have. So even this is too less, but it is still fine. So even you can just still have it as 0.1 millisecond, or you can have it as 0.2 millisecond, because that will be less than so and so. Now if I use okay, let us, when we actually simulate, let us see what happens. Now this type of trigger signal is converted to these type of spikes, and you can see this is 5 volt, and since there is a swing of almost 10 volts, so from this 5 it goes up to another 10 volt swing, it will go up to 15 volts. if I don't use any more circuitry. Now this will affect my further circuit. So what I'll do is I will connect a diode in this fashion so that it will going to clamp the waveform. So it will not allow this to go beyond 5.6 or 5.7 volts. The intention is it is to just take out these type of signals. So once you give this signal which is less than VTL, then what happens? My output which was there at stable state, it goes to quasi-stable state, remains for a period of 1.1 RT/CT. So which is in this case given by, I think it is 10K and 2.2K. So it is 0.2 microfarad, 0.2 exponential minus 6 into 10 exponential 3 into 1.1. So it will be, okay, if I just do it, it is 22 millisecond. Is it? Okay, let me just, no, that is, sorry, 0.2 exponential minus 6 into, actually it is 2.2. Into 10 exponential 3 into 1.1. So it's actually 2.2 millisecond. And when you give the next trigger signal, of course, let us, this is coming after 4 millisecond. So the timing is slightly, so this is having only 2.2 millisecond. So this is the time what you have. So this has got a time of only 2 milliseconds. So your next trigger signal comes after 4 milliseconds. So it just comes maybe after 4 milliseconds. So it just comes here, then it goes there, and it again comes here. So this is how, between this it is 4 millisecond, between this it is again 4 millisecond. Let us see that. So let me run this. This is my square wave, and this is my, okay, let me just for the time being take out this diode. I'll take out this diode and see what is the waveform. So now this is, I've taken out the diode. You can see there is a spike coming. Can you see there is a spike? Okay, let me just slightly increase the value of this R so that it is, you can still see it as a spike like thing. See that? So this is the spike. Okay, let me change the color to a different one so that it is visible. Okay, now can you see this is the spike? Even if it is, now again we are trying to ensure that RC is still less than T. So if you maintain this condition, you can see there is a spike. You can see this is clamped at around 5 volt, and as I said, this will go up to another 10 volts, that is 5 plus 10 is 15. So it is going up to 15 volts. So that's what I said here. It will go up to 15 volts. If I put the diode, it will be get restricted to 5.6. So now what I'll do, I'll go back to my circuit. I'll just do, okay, I'll again make this 10K, and if I run it, see now, can you see this is now restricted to, can you see now this is not going up to 15, so it's now restricted to 5.6, close to that voltage. So, and you can see this is certainly going below VTL, which is 1.66, so this is going to trigger the waveform. Now let us see what is the output is. So this is my output. So this is the output. Let me just put them in different panes. So this is the output. See now, let me change the color. I will change the color to something different here. Fine. See now, when the trigger signal goes below VTL, the output is going to high state. So this is high. This is for a period of 2.2 millisecond. You can actually measure the time. So measure the time from here to here. You can see it's almost 2.2 millisecond. See here, it is 2.2 millisecond. So if you carefully adjust that, it is very close to 2.2 millisecond. This is the monoshot output. You can also see the capacitor charging, discharging. Where is this? Okay, I can see that also. So for that I need to see the voltage in this one. See now, can you see the capacitor voltage charging, and this is going up to 2/3 VCC, and then it comes down. So this repeats. This is used as the reset signal for this stable multivibrator. So as long as this is high, this will be oscillating. The moment this becomes 0, that is reset becomes 0, it will reset the output. so we will see that output also. Now you can see this, you can just click on this, see now. So if you carefully observe this, okay, let me take out this capacitor voltage, let me take out this capacitor voltage. Now you can see, so this is my trigger signal, output has gone high. Okay, let me just put one more pin and then make this. Okay, this is the output of the monoshot. Monoshot output is high, so when it is high, it is oscillating. So this is on time, off time, on time, off time, this is repeating. The moment this goes to 0, whatever the condition of your output is, immediately it becomes, output becomes 0. If you carefully notice, again, charging, discharging of the timing capacitor of a stable multivibrator. So let me see it here. Okay, I'll just pull this down to this. Now you can see, let me change this color to a different one. Okay, maybe this. Okay, see now, the capacitor is charging up to 2/3 VCC and it is going down to 1/3 VCC. That's what is the swing of your capacitor voltage in a stable multivibrator, except for the first cycle. So in the first cycle, it is actually starting from 0, because by that time the capacitor is fully discharged to 0. Now only the first on time is different compared to the rest of the on times, because this is actually starting from 0 to 2/3 VCC. It will go up to 2/3 VCC, but other subsequent on times are from 1/3 to 2/3 VCC. So keep this in mind. So what is actually happening in this is, you are applying a trigger signal which is going below VTL. Once it goes below VTL, even if you make it 1K, there is no issue. It will be much more sharper. That's the only thing. You can see it has become much more sharp. So this is sharp. Again, the output remains the same. So output is still, for 2.2 millisecond it is on, and then this overall output goes off because reset is becoming 0. Okay, fine. So let us see the next one. So next one is, let me see, square wave generator. So this is a square wave generator being configured with duty cycle other than 50%. Now you can see we have two diodes. Diode 1 will be on when output voltage is plus Vsat, because plus Vsat will make D1 as forward biased. During negative half cycle, that is when the output is minus Vsat, D2 is forward biased. So the discharging is happening through 8K. The charging is happening through 81K. So naturally the on time, that is charging time, is more compared to the discharging time. You can actually verify the on time, off time, all those stuff. Suppose if I just run it now, let me close this, let me save this. Okay, fine. Now this is my output. Okay, what is the issue? The issue is there with okay, let me give some initial voltage. IC is equal to 0.1. Let me initialize that with some voltage, because I need to initialize with some voltage. If I don't give any initial condition, it won't happen. Let me have a bit more higher frequency. Okay, let me just go with low frequency, because now let me do this with 1 microfarad. Why you are not getting the proper square wave was because the slew rate of this op amp is very poor. Okay, now that's why I have actually increased the frequency, increase the time period, so that frequency is reduced. So what I'll do is, let me just make this now maybe 50 millisecond, run it. No, this is fine. Maybe slightly more, or let me change the op amp itself. If I change the op amp with a better op amp, where is this? It's here, op amp. You can see this is a precision. If you go for this, this is fine. Let me go for this is low noise, and this is okay, dual. Let me just look for this. Okay, let me delete this. Where is the file? 7. Let me take this and then put this here. Now let us still go with the lower value of C, which was, what was the value? It was 0.1. Now let me run this. Okay, this is fine. Now you have suppose let us also see the capacitor charging, discharging. See, now this is how the capacitor is charging, discharging. So capacitor charges up to beta Vsat. So Vsat here is how much? 13.84. Beta Vsat here will be, because if you can look at this circuit diagram, the beta is actually half. Beta is nothing but R2 by R1 plus R2, because both are 1K, beta is half. So this will be, okay, let me just go there. What is this voltage? So this voltage at this point is 13.8. The capacitor voltage will be going up to half of that, that is 6 point, okay, let me see what is that voltage. So it is, can you see the voltage is very close to 6.7, which corresponds to 13.8 into half. 13.8 into half is this. So similarly, in the negative half, it will be going up to almost minus 6 point. Okay, why it is minus 7.5 is, let us see what is the negative voltage of minus Vsat. So this is on capacitor. Let me just find out what it is. Can you see, since it is minus 14 something, this is minus 14, minus 14.2, so that will be 7.1 or 7.2. So you can see that's why it is, you can see it is almost there at, so actually that voltage will be half of that. So it's happening because, okay, let me just make this, how do I make, okay, fine. Suppose if you increase this capacitance value to 1 microfarad, then the frequency will reduce. You can just simulate for more time, and then you can see this. So this is how the output looks like. You can see this is on time, off time. So on time is more compared to off time, because it is 81K and 8K. So it's interesting to observe the capacitor voltage is always half of the voltage. Suppose if you change this R1, R2, then the capacitor voltage will change, which will actually change your frequency as well as the duty cycle. Duty cycle will be changed by changing the value of this R5 and R3, which is the charging. Okay, this is the charging resistor which will decide your R on. This is the discharging resistor which will decide T off. This is for T on, this is for T off. Okay, let us see one more, that is binary weighted DAC. Let me just take on this, save this. Okay, we know that in this binary weighted DAC, we are supposed to get an output voltage which is minus RF by R. Okay, R, V reference B1 by 2 plus B2 by 4 plus B3 by 8. So we need to give different combinations for this B1, B2, B3. So this is B1, B2, B3. B1 is MSB. So we have to give all different 8 combinations. 1 0 1 1 1 0 1 1 1. So instead of giving these combinations one by one, we can actually generate all these in a pattern like thing, where you can have a square wave of different duty cycles and frequency, 50% duty cycle and different frequency you can able to get. So this is, okay, let me write it in different color. This is one, this is the other one, and this is, if you carefully write the combinations, can you see it is 0 0 0, this is actually B3, B2, B1. Now it is 1 0 0 0 1 0 1 1 0 0 0 1 1 0 1 0 1 0 1 1 1. So this is all 8 combinations will be covered if you apply 3 square waves of a different frequency. Of course, when it is different frequency, it's actually half of this. So if this is f1, this is actually f1 by 2, this is actually f1 by 4. So the frequencies are actually going by divided by 2 divided by 2. And let us see what happens to this. So as per this, so we are supposed to get 0 voltage here. This should be 1 LSB, this should be 2 LSB, 3 LSB, 4 LSB, 5 LSB, 6 LSB, 7 LSB. So 1 LSB in this case is, okay, since it is, I think we have RF and R as same here. Let me just check out. Okay, this is your RF and 2R is 1K. Sorry, 2R is 2K. So this R becomes 1K here. RF is also 1K. So these two values are 1K, 1K now. So these two are 1K, 1K. So 1 LSB is minus 5 into 1 by 8. So it will be 0.625 volts. So it will be minus, so it is 5 by 8, 0.625 volts. So let us see what are the, so now you can see here, this is a pulse. If I just double click on this, you can see this is initial voltage 0 and it is 5 volt, and of course this is rise time, fall time very small. You can see the on time is 1 millisecond, this is 2 millisecond, and this is the LSB. The next MSB is, you can see, since here on time is 1 millisecond, here it is 2 millisecond total time. Here the on time becomes 2, total time is 4. So it's exactly like this. So this was 1 millisecond, whole thing was 2 millisecond. Now it is 2 millisecond on time. This is entire thing is 4 millisecond. So here on time is 4 millisecond. The entire period is 8 millisecond. So this is how the timings have been specified here. This is 1 and 2, this is 2 and 4, this is 4 and 8. So the first parameter is on time, the second parameter is total time. So on time, total time, on time, total time. That's what you can see here. This is on T period. If I apply this and then run, let us see what is this B1. Can you see this is B1 going this way? See B2. So you can see this frequency, you can just put it in different pane. See, this is B2 with double the frequency. Sorry, half the frequency. Of course, this is highest frequency. This is okay. Now B2, which is okay. B1 is MSB. B1 is MSB. And let me see what is this. So this is my B3. B3 is LSB. Should have highest frequency. Okay, let me put one more pin here. Let me put this now. You can see this is 1 milli. Total time is 2 milli. Here it is 2 milli. Total time is 4 milli. Here this is 4 milli. Total time is 8 milli. If I see the output, I will again apply one more pin. I'll see the output here. See now, this is actually 0 0 0. When it is 0 0 0, output is also 0. Can you see your output? Can you see output is, this is, okay, this is actually 0.33 femtovolt. Don't we get worried about this 0.399. It's not volt, it's actually femtovolt. This is femtovolt, means almost 0. For 0 0 0, you are supposed to get 0. Now you can see the combination. This is actually B3 is 1, this is 0, this is 0. It's actually 0 0, this is 0 0 1. So for that you are supposed to get 625 millivolt. You are getting, of course, minus 625 millivolt. You are getting that. That is 1 LSB. Can you see this is 2 LSB, which is 1.25. Can you see this is 3 LSB? 3 LSB is 3 into 0.625, which is minus 1.875. Can you see this is 4 LSB, which is minus 2.5. You are almost there. Then it goes that way. So this is called as staircase generator. This is 0 LSB, this is 7 LSBs. So 7 into 0.625 is around 4 minus 4.375. So this is the voltage. Okay, this is if you generate, if you apply a signal of different frequencies with appropriate condition, so that you can combine all 8 combinations this way. So these are all 8 combinations covered by these 3 waveforms, and you can verify the what is that output waveform. Okay, thank you.